Travel time towards BH horizon. Let us consider the situation of observer A, Alice, whose frame of reference is in a radial free fall, L equals 0 towards the BH horizon, 4. A's frame, or spaceship, initially was at rest at a mother station Mississippi, located at R0. The coordinate time to cover the radial coordinate range R0 in this case is found from EX 6-9. It diverges, t as A's spaceship approaches the horizon, RR. The proper time, which is the time measured by Alice herself, turns out to be finite. This illustrates a manifestation of the most dramatic time delay, for distant observers, but actually for all observers exterior to the horizon. Alice's frame of reference would need an infinite time to reach the event horizon, while a finite time elapses for the co-moving observer, Alice herself. Another aspect of this outcome has already been mentioned. The speed, v, of the freely falling test particle as measured by a static observer, so, follows from the expression, see also. One finds then a general outcome, the speed of a test particle radially freely falling, approaching the event horizon tends to the value of the speed of light in the vacuum. And this result is independent of the initial conditions. One may ask, how would that speed be changing inside the horizon? We discuss this question subsequently. Generalized Doppler shift, how to fix the instant of crossing of the Schwarzschild BH horizon. It is a well-known fact that due to the equivalence principle, an observer confined within a frame freely falling towards the horizon cannot identify the instant at which he or she crosses the horizon, and if a black hole is large enough, such an observer would harmlessly cross the horizon without even noticing. On the other hand, one can quite precisely determine that instant. How is this seeming contradiction possible? Before resolving this, let us recollect a well-known result, that of the gravitational frequency shift. In order to do this, one considers radial signals of a fixed frequency, omega macron emitted at R0, the location of the mother station, and recorded by a static observer at R greater than R. The wave vector k of those radial light rays, k equals ktkroo is, Cx 6, 7, where plus or minus corresponds to out and ingoing rays, respectively. If ms emits such a signal with frequency, so records it at R and measures its frequency as so, O. The frequency recorded by so is indefinitely blue-shifted, when R tends to R, f0. When such radial signals are recorded by Alice, omega A equals uak, at her instantaneous position at R, then she finds, Cx 6-9, and 15, 16 where v is the speed of her spaceship as measured by so, placed at R, C, 14. Exchanging such signals, one can observe a generalized Doppler shift of the following form. And the meaning of result 22 is as follows: signals coming from a frame in falling towards the black hole horizon are indefinitely redshifted, and ultimately disappear from the screen/sensors. Such a journey seems to take infinitely long for external observers. This confirms our former conclusion. The result, 21, on the other hand means that the Doppler shift of signals coming from ms allows Alice to identify the horizon quite precisely. The Doppler shift reaches a value of half on the horizon.